module 4, we have been looking at protein isolation and characterization methods. What we will do in this lecture is look at some of the biophysical methods that are involved in the characterization as well as in the isolation procedures to understand whether we have our protein of interest. The concepts that are going to be covered are the specific spectroscopic methods associated with these types of characterizations in terms of UV visible spectra, infrared, circular dichroism spectra. And what we understand is what we have seen before also, the protein chromophores, how we would know that we would have a spectroscopic signal associated with the proteins, and specific vibrational modes in terms of the IR spectroscopy techniques, and what we look at for circularly polarized light. So, in the spectroscopic characterization of proteins, we have looked at, or there are methodologies that are going to tell us about the size, shape and the detection of the secondary and the tertiary conformations. It is important we know for the proper functioning of the protein to have the proper structure of the protein. So, to know that the secondary structure elements or the tertiary conformation of the protein are in their correct three-dimensional conformation is important, and some of these aspects can be identified or can be determined by these specific spectroscopic techniques. The quantification of proteins in terms of finding out their concentrations is something that we have looked at in a previous lecture related to the amino acids, where we identified the specific amino acids that can comprise the protein chromophoric units. In addition, when we will be looking at protein ligand interactions and protein-protein interactions, these spectroscopic aspects are extremely important to understand the binding characteristics and to give us some idea of the affinity of the ligand or the protein to other molecules. So, when we look at the spectroscopic methods that are important or are utilized in an understanding, we have the UV visible, the FTIR, circular dichroism, fluorescence, DLS, SAX and NMR. Now, each of these have their own particular spectroscopic characteristics, and they can be used for specific identification and characterization and determination of specific information, or they provide us with specific information, and the resolutions are such that if we are looking for low resolution, we can look for UV visible, DLS and fluorescence. We are not talking about sensitivity. Sensitivity is very high for these methodologies, but the resolution of the structure analysis that we can use here is then low and then medium for FTIR and CD and very high for X-ray diffraction at NMR, because we are looking at the specific atoms and the specific local environments for the structures. If we look at the UV visible absorption of biomolecules, as we looked at, we had the UV spectra in water. Now, considering that most of the protein solutions that we make are in a buffer solution, we have no vibrational structure as then, but we have the peptide bond that is also a chromophoric moiety in formation of the amide chromophore. So, the strong polarity of the water molecule sometimes gives us a broad spectra with no vibrational structure per se, because with the water the energies of the individual solute molecules, they will differ from one another. But nevertheless, we do get specific information. We know that the protein chromophores themselves can be divided into the amide chromophore, that is the peptide bond itself, and the amino acid side chain, and we have two strong bands here, one at 190 nanometer and the other at 210 to 220 nanometer. That is essentially a forbidden transition. But nevertheless, we have information from these aromatic side chains and cysteine, the disulfide bond formation that is formed between two cysteine amino acid residues. These are the specific chromophoric moieties where we can use for information, for knowledge based information about our proteins. The peptide bond absorption is not really usable, but the tryptophan absorption, having a very high extinction, which we learned before, is very important, in addition to tyrosine, phenylalanine and cysteine, that also show appreciable UV absorption above 250 nanometers. If we look at infrared spectroscopy, now each of the spectroscopic methods that we are briefly touching upon here will be shown in their specific aspects in an understanding as and when we study specific techniques and specific ideas related to the subject or the topic at hand. When we are looking at infrared spectroscopy, we have normal modes and we have what are called stretching and bending of these bonds. Now, this stretching and bending is going to give rise to the vibrational spectroscopy, and the stretch in the amide, we know that we have C double bond O and NH. In the stretching of the primary amides, there are variations when we have, say, hydrogen bond formation. So, that is an indication that tells us that we are going to have some information given to us. So, whether we have a free C double bond O NH or whether it is involved in hydrogen bonding, where we are going to have variations in their frequencies depending upon what type of interaction they are involved in, that is what we can determine from IR spectroscopy. So, we have the stretching and the bending modes that are important. In case of proteins, we have the major group vibrations because of the protein backbone. And what is the information that we have in the protein backbone? We have the C double bond O and the NH, a hydrogen bond formation that is possible, and nevertheless they can go through specific amide interactions in addition to the hydrogen bonding between them. So, the amide bonds or the amide bands here actually reflect the global conformational change. So, we have amides A and B that comprise the NH stretch that is seen at 3100 and 3300 wave number, that is given in centimeter inverse, and amide 1 that corresponds to the C double bond O stretch. So, variations in the NH and the CO stretch give us indication that there are some interactions involved. So, what we have is the interactions we know in terms of CO and NH are possibly hydrogen bonding interactions, and where do we see these primarily? We see them in protein secondary structures. So, even though the correlation is not absolute, we do have alpha helix interactions where we can see them ranging from 1660 to 1648 centimeter inverse, and for the beta sheet from 1640 to 1625 centimeter inverse. Now, we have turns and we have other unordered peptides. So, depending upon where their appearance is in our specific spectra, we can actually identify what kind of secondary structure we do have. For example, the amide 2, we have the amide 1 and the amide 2 that are mostly important for our protein determinations, and what we look at for here is we are looking at this region of the amide 1 and the amide 2 spanning from 1700 to around 1500 centimeter inverse is what we are interested in. So, this information tells us that when we have the amide 2, we have mostly an NH bend and a CN stretch. So, we are looking at the backbone information that is provided through with the IR spectra. So, we have a very sensitive to the HD exchange. So, we use this along with the amide 1 to check solvent accessibility, where we look at H2O, D2O, HD exchange, because we have our solution, our protein in D2O. We will look at these when we go to specific interactions, when we look at, say, protein ligand interactions or determinations of other types of interactions. So, we can actually look at the protein core, and it is also available to look at, or rather information to give us about the unordered and the helical conformations. So, this information is important because we are now looking at a C double bond O. We have the stretching that could be important here, and for the amide 2 we have NH bending and CN stretching, and the amide 1 will give us the stretching for is what we saw here, the amide 1, the CO stretch, that is important. So, this information provides us with information about the specific type of secondary structures that may be present. So, when we are looking at the amide bond, as we looked at the amide 1, that is the CO stretching, we looked at the amide 2 that corresponds to the NH bending. So, when we are looking at the CO stretching, we have the CN stretching, the NH bending, the CN stretching and the NH bending, then out of plane bending that is also possible, that gives us information about the specific interactions that are involved. For proteins, we look primarily at the amide 1 and the amide 2. So, the amide 1 band for the polypeptides is sensitive to the secondary structure, and this gives us a relation between the structure and the spectra that we can obtain for the specific protein. Another type of spectroscopy that is used very often is circular dichroism. Now, circular dichroism spectroscopy is again usually a method for assessing the common secondary structure and monitoring the folding in proteins. So, if we know that our protein is correctly folded, the content in terms of secondary structure, the alpha helical content, the beta sheet content is going to give us a specific value. So, we can actually quantitatively get the percentage, say, of the alpha helix in the protein. An understanding of the structure, a knowledge of the structure is essential, therefore, from a structural standpoint in terms of its function, because we know that if the protein has to function correctly, it has to be folded correctly. If it is folded correctly, then its secondary structural elements are in their correct conformations and they have a specific content, secondary structural content in their structure. So, any form of structural asymmetry in a molecule gives rise to differences in left-handed versus right-handed circularly polarized light. We will see what we mean by these terms in the couple of slides later on, and the difference is called circular dichroism. So, if we look at the superposition of two plane polarized waves with orthogonal polarizations, but with a phase shift, we have this as the right circularly polarized light and this as the left circularly polarized light. Now, when we are looking at any polarized light, we see that the left and the right, when superimposed, it is going to give us linear circularized light. So, the important aspect here is we have two plane polarized waves that have orthogonal polarizations. If we look at the animations here and we look at the rotation, so we have the red and the green, and the red and the green here. The red and the green, when combined, give us the right circularly polarized light for the one on the left, and what we see here is we see again the superposition with a phase shift that is going to give us left circularly polarized light. Now, what happens is we are looking at the difference between the absorption of left and right handed circularly polarized light, and this is measured as a function of the wavelength. This circular dichroism is measured as a quantity called the mean residual ellipticity, whose units are given here. So, what we have is we have absorption giving us some different spectra, that is a manifestation of the subsample through which this light has been passed through. So, when we are looking at right polarized light, that is going to be traveling in this direction shown by the arrow here, or left polarized light that is going to be following the arrow on the left hand side, the summation of this is going to give us this linear light. Now, what happens is, if our sample absorbs the light differently. So, essentially what we have is we have linear polarized light. This is viewed as a superposition of the opposite circularly polarized lights which are of equal amplitude and phase. So, if we have the right circularly polarized light and the left circularly polarized light and they are superposed, what we get is we get linear polarized light. Now, if our sample is such that it absorbs preferentially one particular type of light, so resulting in different absorption of the left and the right handed polarized light, what happens then is we can see here the left component is the same as it was originally, but the right component, part of the right component has been absorbed. As a result of what has happened, we now have ellipticity because of a specific some component in our material. It's called a rotational absorption that we're looking at here. So, we're looking at this substance or this sample, in this case our protein, that has preferentially absorbed the right circularly polarized light and not the left, as a result of which we have got ellipticity. So, if we look at the circular dichroism of proteins, the CD spectra that is found between 260 and approximately 180 nanometer can be analyzed for the different secondary structural types. So, we can look at the characteristic spectra, CD spectra of a protein and distinguish alpha helix, parallel and anti-parallel beta sheets, turns and other random structures. So, the identification of an alpha helix tells us a lot of information about the protein in terms of its secondary structural units. So, in fact, the modern secondary structure determination by circular dichroism actually can achieve accuracies of up to 97% for helices and 75% for beta sheets. So, the importance here is the CD signal. So, when we are looking at the CD signal, we look at the proteins. We are mainly concerned with the absorption in the ultraviolet region of the spectrum. Now, we are looking at the peptide bonds, because the symmetric chromophores and also the amino acid side chains, but here we are looking at the peptide bond that we form between the C double bond O we know and the NH. So, when we have a peptide bond formation or we are looking at specific rotational strength because of say helix formation or hydrogen bond formation, we are going to have specific hydrogen bond formation because of the specific geometry that we can see for these molecules. So, when we are looking at the specific geometry of the molecules, we know that the alpha helix and the beta sheet have specific geometry. So, the protein chromophores in this case are the peptide bond and the amino acid side chains. So, the lowest energy transition in the peptide chromophore is an N to pi star transition, which we had observed or we had discussed earlier in our discussion for the peptide bond and its spectral characteristics. So, if we are looking at the peptide bond, so here is our peptide bond. So, we are looking at a transition from an N to pi star. So, we are looking at an N pi to pi star transitions, means we are looking at this transition, and N to pi star means we are looking at this transition. So, a pi to pi star transition is going to be one that is going to be of a lower wavelength, and an N to pi star transition, the energy gap being lower, is going to correspond to a larger wavelength. So, what we can get from this information is different secondary structures of the peptide bonds have different relative intensity of their N to pi star transitions. And what happens? This results in different CD spectra, and the CD is extremely sensitive to the change in the secondary structure of the proteins, and it is very commonly used to monitor the conformational change of the proteins. And the helical content of the peptides and proteins is estimated by a signal at 222 nanometer as well as 208 nanometers. So, when we look at a CD spectra, it is very easy to identify the specific characteristics of the secondary structure because we have the relative intensity from the N to pi star transitions that are being monitored in our specific spectra. So, there are several curve fitting algorithms that are used that actually are used to deconvolute the relative secondary structure of proteins, and these are actually given by the specific CD spectroscope, the CD machines that we use, and we are looking at the far UV spectra and what do we see. So, this is the typical spectra that we see. So, we will have a band here at 190, we know that this corresponds to the, let us go back, this 190 corresponds to the pi to pi star. When we are looking at the other region here, typically when we have this a negative band here at 222 and 208, this is characteristic of an alpha helix. So, here is the alpha helix where we have the 208 and the 222. If we look at the beta sheet, this will be where we have this around 217 nanometer. Now, when we have a protein that has a combination of an alpha and a beta structure, we will see some combination. So, this is a typical alpha helical structure. Then we will look at the characteristic spectra that we observe, where we can see variations of the spectra because of the differential content of the secondary structural components that are present in the protein. So, the idea of using UV visible absorption spectroscopy, that is going to give us, say, the concentration of the protein. It is going to give us relations related to the presence of a protein. So, when we have studied the protein chromatographic techniques where we have looked at the isolation of proteins, we detected the presence of proteins using UV absorption spectroscopy, because we know that the presence of the aromatic amino acids residues or any chromophoric moiety is going to give rise to the UV spectrum. When we look at the specific vibrational spectroscopy, we are looking for specific characteristics in terms of the stretching and the bending modes of the bonds. And when we term this as looking at secondary structural elements, we are looking at the C double bond O and the NH. This information is important because any interaction associated with the backbone is going to have an effect on the overall conformation of the protein. That is going to obviously affect the structure of the protein. And we know that since the structure and the function are related, any variations in the structure is going to amount to a variation in the functional characteristics of the protein. So, an idea of looking at, say, the secondary structure component, which is an important part of a folded protein, is going to give us information that we would require to see whether we have the correctly folded structure. So, when we are looking at the IR spectra, we are looking at the amide 1 and the amide 2. The information from these CO stretching and the NH bending and the NH stretching gives us information about whether there are any variations. So, now if we have a specific technique or we are looking at the unfolding of a protein, then as we saw in the protein denaturation techniques, when we are trying to understand whether we have the folded protein or the unfolded protein, there were specific spectroscopic characteristics that we could look at to monitor this effect. So, we could look at IR variations, we could look at UV variations, and now we see that we can look at also our circular dichroism variations that will tell us that there is a disruption in the protein structure because of denaturating conditions. So, the three aromatic side chains that occur in proteins, the phenylalanine that has the phenyl group, the phenolic group of tyrosine, that's the OH, and the indole group of tryptophan, they also have absorption bands in the UV spectrum, as we were just discussing. So, the aromatic residues, if unusually abundant, sometimes have effects on the CD spectra, but nevertheless this is more of the transitions that we spoke about. In addition, the disulfide group, which is also we know is an inherently asymmetric chromophore because it prefers a gauche conformation with a broad CD absorption around 250 nanometer, but the range that we are looking at is between, as we saw in the CD spectra before, is somewhere around this region. So, now each of the three basic secondary structures, then the helix, the sheet and the coil, show a characteristic CD spectrum, and this is the CD spectrum of the proteins, and this can be deconvoluted into three individual contributions. So, we can say that this is the alpha helical content, this is the beta sheet content, and this is the content of random coil, and any variations related to protein ligand interactions, protein protein interactions, or even protein unfolding can be detected from these methodologies. The books that this is the place where from the animation, there are many other animations that can be looked at. The books Cantor and Schimmel and Voigt and Pratt. Thank you.